what we're going to be doing for a video is taking one of the problems from the WebWorks and solving it. So what the problem asks for is the tension in the scale A. Now the problem's about is two scales A and B that are attached to a weightless pole, which to it are attached three weights: X, Y, and Z. Now we do not know the weight of Z, okay? Nor do we know the tension in B, and we are asked to find the tension in A. But we are given the weight of X, which is actually 0.94 kilograms, the weight of Y, which is 2.18 kilograms, and the distance between A and X, X and Y and Z. We're going to be using summations of torques equals 0. Now, in order to make it easy for us, we're actually going to set the hinge over here, because we have no data over B and Z. So in order to make the torques cancel, we're going to set the hinge right at where they are, because like that, the radius is going to be equal to 0, which makes the formula for torque being equal to RF sine theta. It's going to make the R equal to 0. Okay. So, let's do the torques. Now, we have, pretty much by convention, this is a pivot, and whatever spins clockwise around it, rather clockwise like this around the pivot, is defined as negative, and whatever spins anti-clockwise can be defined as positive. So, clockwise, right here, this would be negative, and anti-clockwise is positive. Alright, so we have torque of A, torque of X, and torque of Y. So, now, because we defined A as going negative, because it's pulling that way, tension pulling up, doing a circle towards the negative direction, we would have minus torque A, minus torque A plus torque X plus torque Y equals to 0. Alright, Chris, up to you.
Okay. So now that we've set up our whole equation, we can actually replace the values by the different objects that we're trying to find the torque for. So for the torque of A, we have the total distance of the actual bar. Because when we look at the radius, for the radius it has to be from the pivot point. When we take the radius, it has to be from the pivot point to wherever we're taking the actual torque. So in this case, it's going to be, the radius is going to be 0.8 plus 0.9 plus 0.5 meters.
0.05.
0.05, sorry. So for this, it's going to be negative 0.05 plus 0.09 plus 0.08, because we know that our formula is RF sine theta, so then we need the force. That's what we're looking for. So we're just going to leave it as a letter instead of the actual force, because we have to solve for it. What else are we looking for? Oh, and plus the angle, sorry. In this case, the angle is 90, because the sine of this right here would be 90. And sine of 90 is 1. So, to be quite honest, we can just write it as 1, multiplied by 1. Or, to make our lives easier, we won't even put it there. So to continue from where we had just left off, we were determining the torque of the X block. To find out the torque of the X block, we have to know the distance, which it's like how far it is from the actual pivot point that we've set up. And in this case, it would be 0.08 plus 0.09 meters away from the pivot point. So that's what we would set as our radius for our torque equation. Now for our force is actually the weight of the X block. So the weight of the X block is equal to 9.8, which is gravitational acceleration, multiply by our value in kilograms for the the mass of x. So in this case, it's going to be 0.94 multiplied by 9.81, which gives us 9.22 newtons. And then we multiply that by the sine theta, which is the angle. But in this case, our angle is actually 90. So what's the sine of 90? 1. So now that we just dealt with our torque of our x block, now we can also find the torque of our y block. Same idea. We are given the distance, so as our radius, all we know, well, from the pivot point, is 0.08. So it's just going to be 0.08 meters multiplied by the force, which is once again the weight of y, and then multiplied by the angle which it's being held by, which is 90 degrees once again. So it's just going to be multiplied by 1. So then for our weight of our y, we're going to take 2.18, which is the mass of the y block, and multiply that by the gravitational constant 9.81. So it's going to be 2.18 multiplied by 9.81, which is 21.38 newtons. And this all multiplied by 1 because, well, the sine of 90 is 1. So let's set up our equation. We're trying to find the force which the scale of A is reading in this case. So what is the only the only unknown in this equation at the very moment? It's force. So we can set this up in a way that we can solve for force. Simple as just moving certain things over, because this is all equal to 0, by the way. So we can just move over the F on the other side, and then add these two scalar values together, and then divide them by the value of F, which will give us our force, which is read by the scale of A. So let's do that. First of all, I'm just gonna combine this. I'm not gonna I'm just gonna do it. I'm gonna make this simple and make it clean. I'll just add these two values together. So what we're gonna do is multiply 0.17 times 9.22 plus 0.08 times 21.38. So this is going to give us 3.27 is equal to, now we're going to bring the F to the other side of the equation, so it's going to become positive. So this will be 0.05 plus 0.09 plus 0.08, which I think is going to be 0.22, which it is. And now, we just solve for F. So our force is actually going to equal to 3.27 divided by 0.22, which gives us 14.86 newtons as the force read on scale A.
9.212. I'm sorry, Chris.